As we continue to discuss the mechanics of a single composite layer, in this video we're going to try to relate the stress and the strain within that layer. So we said in the first section of the notes here that both stress and strain are second order tensors, and just by using that and saying that any stress can be related to any strain by some quantity, we can write this expression. And so that value C in the middle would be a fourth order tensor. In other words, could have up to 81 numbers there. Well, of course, a lot of those would be zero, but that's a lot of numbers. So one of the advantages of using contracted notation, where we said instead of 9 quantities of stress and strain, that there are only 6 independent components. And so we wrote those then as such that the stress and strains can be defined by sigma I and epsilon I, where I goes from 1 to 6. And that means that our matrix in the middle there that relates to stress and strains is a 6 by 6 matrix. So we can write this as such: sigma I is equal to Cij times epsilon j, where j can be from 1 to 6. Now, we're going to see that the C matrix is symmetric, and to prove that, we use a concept from solid mechanics called strain energy density. And if a material has a linear response, then the area under the stress strain diagram would be triangular and would have the quantity shown here, 1/2 of stress times strain. And of course, all of the stresses and strains would contribute to the total strain energy. Okay, well, if you look at the stress-strain equation on the top of this page and we substitute that in for stress, you can see here's our expression then for the strain energy density. And now we can take derivatives of that. We can take a partial derivative with respect to epsilon I, and then taking the second derivative this time with respect to epsilon j, and we find that's equal to 1/2 times Cij. So that's one way you can define those C values, those stiffness values as we'll call them, is that it's related to the derivatives of the strain energy. Well, that's not too important to us right now, but what is important is you can see that if we went through that same argument and found Cji, that those two are actually identical because the order in which you take the differentiation is not important. So Cji is equal to Cij. Again, what that means is that C matrix is indeed symmetric. So instead of 36 independent constants, there could be up to 21 when we consider just the diagonals in the upper portion of that matrix. And so if we talk about a triclinic material defined as being the material axis oblique to each other, or another way of saying that is that there are no planes of symmetry for this purely 3D material, the C matrix we call the stiffness matrix. And when we invert it, it's the compliance matrix, and we give that the designation S. I don't know why stiffness is C and compliance is S. Don't blame me. I didn't come up with that nomenclature, but that's pretty common. Okay. Let's find some of these elements first. Let's start with the compliance matrix because it's easier to think of what these terms mean rather than the stiffness ones directly. So again, just the sim down in the corner just means, hey, this is symmetric. So there are, as we stated here, up to 21 constants here. And because of the fact that the C matrix is, we showed that is symmetric, that means that the compliance matrix S has to be symmetric as well, because if you have a symmetric matrix and you take its inverse, the inverse will be symmetric as well. Now, let's take a look at the first equation there, which was that epsilon x is related to all of the stresses, sigma x, sigma y, sigma z, etc. And the first term of that, S11 times sigma x, we would call that, well, that's a direct extension. In other words, it's relating the stress in the x direction to the strain in the x direction. All of those other ones represent some sort of coupling effects. So you look at S12. It says, okay, if I have a stress in the y direction, I'm going to have a strain in the x. Well, that's a Poisson's ratio effect. And similarly, you can have those coupling effects between all of the other stresses and the strain in the x direction. So going back to our our compliance matrix S, we can map on there the coupling effects. So we start out by saying along the diagonal, these represent the normal stress to the normal strain. So we would call those direct extension. Further along the diagonal, those those relate shear stress to shear strain in the same plane, and so we call those direct shear. Up in this corner, there's your Poisson's ratio term, so that we call that extension-extension coupling. Stretch it in one direction, it stretches or contracts in the other direction. Similarly, there's a similar kind of phenomenon taking place between shear stresses, similar to Poisson's ratio effects. And this entire upper block here is a relationship between extension and shear. So if you pull on something, is it going to have angular changes in any directions? So those are the coupling effects. And as we said, those will all potentially be non-zero for a triclinic material. But now let's take a look at a fiber reinforced material with the fibers in the XY plane. We would call this a monoclinic material because there is a plane of symmetry, a single plane of symmetry, which in this case would be the XY plane. Now if we do that, we would say that there are certain material behaviors that violate the symmetry. If you put a normal stress in the x direction, it's not going to cause a shear strain in the YZ plane, because if it was doing so, that would violate the plane of symmetry. And based on that logic, then the component S14 of the matrix has to equal 0. So if you kind of go through and think about those symmetry conditions, others, you'll find that we can put zeros into a lot of the categories here. And what we end up here for a monoclinic material is a matrix that has 13 constants, independent constants in it. All right, let's go one step further. Let's look at an orthotropic material. Now we're going to align the fibers, and we're going to look just at the mechanics in the 1-2 plane. And in this case, we're saying, okay, if the local and global coordinate systems are the same, we're going to use the 1, 2, 3 system instead of the X, Y, Z to evaluate this orthotropic material. And in that case, you're going to see that, again, because of some symmetry conditions, you get several more zeros here as well. And so now we're down to, as you can see, a total of 9 independent constants within that matrix. And you might, if you're thinking ahead, yeah, what do those 9 represent? It's going to be 3 moduli of elasticity, 3 shear moduli, and 3 Poisson's ratios. But we'll get to that in just a few moments. So it's easy to figure out the terms of the compliance matrix for that orthotropic material. So first of all, let's think about it doing a tensile test where you've aligned all the fibers in the direction of loading. So in other words, you're loading it in the one direction. Well, when you do that, you're going to have and measure strains in all the 1, 2, and 3 directions. You've done, certainly in mechanics of materials, you've done a test like this where you measured strains in the 1 and the 2 direction, but suppose you could measure it in the 3 direction as well. You'd find, of course, that you would relate the strain in the 1 direction to the stress in the 1 direction by the Young's modulus E1. And in the 2 and 3 directions, those would be based on Poisson's ratios. Now you notice the Poisson's ratios have subscripts on them here. We'll define those in just a moment, but you can see those are the relationships between the strains in the 2 and 3 directions and the stress in the 1 direction. And the definition of the Poisson's ratio is like this. If it's Poisson's ratio subscripts ij, means strain in the j direction divided by strain in the I direction for loading in the, I should say, the I direction only. And of course the negative sign there, because a positive Poisson's ratio means that if you stretch it in one direction, it's going to contract in the other. So that's the definition of a Poisson's ratio with subscripts. So if we think about loading in the 2 and the 3 directions, we get a similar set of equations where epsilon 1 in both cases will be based on Poisson's ratios. Epsilon 2 for sigma 2 will just be based on the Young's modulus in the 2 direction, and similarly for epsilon 3 based on sigma 3. And again, all those Poisson's ratios follow the definition we showed earlier. Now for testing material in shear, we'll find, of course, that shear strains are related to shear stress by the shear moduli, and there's no coupling between shear strain. So in other words, we put on this shear stress tau 1,2, it will cause a shear strain gamma 1,2, and the constant of proportionality there is the shear modulus G12. And we have the same thing for shears in the other 2 planes. Okay, we put all that together, and now we have the strain-stress relations between the between the local strains and the local stresses for an orthotropic material. So again, you'll see that there's more than 9 here, but remember this has to be symmetric. So as we'll see in just a moment, there's going to be a relationship between the Poisson's ratios here. So again, 9 independent constants. One thing to remember here is that a fiber reinforced layer is going to be orthotropic with respect to its local coordinate system. Once we rotate it and put it into a kind of a general orientation, it becomes a monoclinic material. And again, the S matrix, the compliance matrix, is symmetric, so that's going to mean that we can write some relationships between the Poisson's ratios. For example, these 2 terms are the same, which means that the value of the Poisson's ratio 2,1 is equal to the ratio of the 2 Young's moduli times Poisson's ratio 1,2. And similar for the other pairs of Poisson's ratios. Now, sometimes you can characterize a material by fewer than those 9 independent constants. As we said earlier, 3 modulus of elasticity, 3 shear moduli, and 3 Poisson's ratios. But sometimes we talk about a composite layer as being transversely isotropic. What that means is that in the 2 and 3 directions, they have the same properties. Now again, that may not be totally true because of the way the material is packed as you compress things together, but generally that's usually close enough. So if you look at the picture here of this layer of material again, so the 2 and 3 directions would be matrix dominated, and if you assume that they are identical, then you can set the modulus E3 equal to modulus E2. Again, Poisson's ratio, shear moduli, you can set a couple of those equal to each other as well. And finally, you can do this. You can apply that relationship between the Young's modulus and the Poisson's ratio in the 2-3 plane and relate that to the shear modulus. And so that gets you down to 5 independent constants. And of course, if you take that one step further and we have an isotropic material, then you can see that now we're down to what looks like 3 independent constants. But remember, there's a relationship between the shear modulus, the Young's modulus, and the Poisson's ratio. So an isotropic material, we say that its material response can be defined by 2 independent constants, just E and nu. And again, when we did this in mechanics of materials, we call this generalized Hooke's law, in this case for a 3D state of stress. Okay, with that in mind, we're going to go back to plane stress next time and get down to stress-strain relations for that layer and be able to rotate them into global coordinates as well.